In this video, I'm going to talk about setting up a projectile motion problem when the variables are given but no numbers. This is a general solution which is intended to help with problem solving in physics. And every problem is just a little bit different, so this is really just intended to get you started. Here we have a ball launched with a starting speed at a known angle relative to the horizon. The ball originates from a platform which we'll call position x0 relative to the ground and lands on a platform that is xf meters above ground level. So first thing we do when we solve problems is we make a useful picture or sketch. And so here we start on a platform relative to the ground and it ends in a platform. I don't really know what's what, but which one's higher, which one's lower, it's not known, but it'll work. We're going to start by indicating the information that we know. We'll call this position right here x0, and we will call this position right here xf. One thing that is wise to do is just to roughly sketch out the trajectory that the ball is going to take. It doesn't have to be perfect, but it should be pretty close. What we're going to want to do is we're going to want to start marking the vectors in their proper direction as they have been given. And some are in the question. So for example, we're told that the starting velocity is in that direction at that angle. And sometimes we can kind of just infer on what the directions the vector's in. If you'll notice on the way down, right as it lands, the ball is taking about that trajectory. So I'm just writing in a sketch, and I'll call that VF. There are many questions on the AP test where they're just asking you to select the arrow or the vector that's facing the right direction at the end. And so this is kind of helpful. For projectile launches, the acceleration vector is pretty easy to figure out, pointing down for Galileo's constant. Now, one that's not quite so obvious is the displacement vector. By definition, the displacement vector is the straight line separation between where the object started and where the object ended. And so it got a little messy there, but this chart is for me, not for anyone else really. Now, the next thing we do after we've made our well-labeled chart is we are going to make our graphs. And as we saw in our lab, the strategy is to deconstruct the initial velocity vector into its horizontal and vertical components. And this is done using right angle trigonometry. So this little vector diagram that I'm drawing right here is just showing the initial velocity vector. And I have broken it up into its x and y components. To figure out the magnitudes of these, we will just use sines and cosines. Once we have deconstructed the initial velocity vector, we're going to make our graphs. And we need one for each dimension. So in the x direction, here's a velocity versus time graph, and in the y direction. Now, as we saw from our lab, that in the horizontal direction, our initial velocity is constant. And we also saw that in the y direction, that our initial velocity is subject to Galileo's constant. And that's the slope of the line. Getting started with a well-labeled graph and a well-labeled sketch is a very important part of solving any problem. In the next video, we'll start adding some numbers and some more specifics to make the problems a little bit more useful for homework and things like that. Thank you.